it's really different. I love teaching it. I know that it can be very challenging and frustrating at times for students and for myself, but it's a break away from all of the algebra, although it does turn algebraic at some point. We're dealing in this unit with three topics: permutations, which we're going to spend 3 lessons on; combinations, which we're going to spend 1 lesson on; and then something called the binomial theorem, which seems to come out of left field, and it doesn't seem to be connected to permutations and combinations, but it turns out it's intimately connected with combinations. Many of the problems that we do, certainly all of the ones that we do over the first 4 lessons, seem to be puzzles. It's about finding out how many different ways things can be completed. And most of what we do in this unit hinges on something called the fundamental counting principle. But before I get to that, I think it's important that we understand the difference between a permutation and a combination before we even learn about anything else. A permutation is an arrangement of items, whereas a combination is a selection of items. And there's a huge difference between those two. If I'm playing poker, and I guess you have to understand a little bit about playing cards in the game of poker, and I'm dealt 5 cards, and they are 3 aces, a king, and a deuce, a 2, I don't care the order in which they were dealt to me. I just care that I have that combination of cards. And that's true of pretty much every card game. I'm sure there's an exception to that. But if I had a lock on a locker, and I know there are 3 numbers that I need to point that pointer to, the order in which I choose those numbers to enter them into the lock or to dial them, the order matters. It's important. Right? If the numbers to the lock on your locker are 5, 20, and 12, you can't just put them in any order. Which means when you look at those numbers on a lock, those are an example of a permutation. Another example of a permutation would be the numbers for your phone number. Right? If my phone number is 387-5225, and you decide, well, I don't care about the order, I'm just going to randomly type those numbers in and expect to get Mr. Way, you're not going to get Mr. Way. By the way, that's not my phone number. I don't know whose phone number that is, okay? Don't bother them. So what's interesting is that all these years you've been using a combination lock, but a combination lock doesn't use combinations, it uses a permutation. So a combination lock is actually a permutation lock because the order in which you dial those numbers matters. Now, what we're going to be doing today is introducing ourselves to something called the fundamental counting principle. And for some reason, people seem to think that the fundamental counting principle is used only maybe for combinations or only maybe for permutations, but it can be used for a lot of different situations. It's a utility device in mathematics to determine how many ways things can happen. And as a warm-up, we're going to be solving problems using the fundamental counting principle, and then we're going to start to just barely apply something called factorial notation. So the warm-up I have is about Bobby Bear, and there used to be a nice website where it was designed for children, and it would say Bobby Bear, and it would be narrated. Bobby Bear is going on a vacation, and Bobby Bear has 2 different shirts and 3 different pairs of pants, and you had to design different outfits. The question was, how many different outfits could Bobby Bear have or wear? And you had this template on the website, and then you would drag over pieces, and it would say, oh, good for you, you made an outfit. And then if you made the same outfit twice, it would say, oops, you already made that outfit. And I really liked using it, but it's a dead website now, so luckily I copied these images over. There's Bobby Bear's outfit. I hope it's not lost on you that the colors of the pants, blue, red, and orange, I've highlighted with bold B, bold R, and bold O. I'm just indicating that those are the different colors. And what we're asked to do is find out how many different styling outfits he actually has. I mean, he packs 5 pieces of clothing, but he packs a number of outfits. And let's assume for the time being that wherever Bobby Bear is going on his vacation, he has to wear pants and a shirt in public, otherwise he'll be arrested, okay? So the question is, how many different outfits can he make, and what are all the different outfits? Now, I don't expect you to draw this, but Bobby Bear could get up on the first day of his vacation and put on his favorite green shirt and then put on red pants over top, and that would be one. So how can we describe that outfit? Well, what you could do is use an ordered pair. I'm going to use the ordered pair pants, comma, shirt. And that would mean that what this ordered pair is R, comma, G, red pants, green shirt. So we're listing all of these. And I am acutely aware that many of you know the answer to this problem already, and many of you could write out all of the combinations of outfits. Because when Bobby Bear goes to his closet in the morning and he picks the pants and the shirt, there's nothing to say that he has to pick those in a particular order, right? He wants this color and this color. Bobby Bear could, on another day, I guess I'll go full screen to give myself another room, say, I really like that green shirt, but he doesn't want to look like a fool and wear the same clothes day after day, so he puts on the blue pants. And this would be blue-green. I don't really think it's important about the ordered pair thing. This is a way that we could list them. This would never be a written response question. This is just learning about the fundamental counting principle. Can he wear the green shirt again? By the way, I'm not sure why there is a second yellow shirt there. Can he wear the green shirt again? Well, yes, because he has his gold or orange colored pants. So that would be a third one. I'll fill in the ordered pair information in a bit, but he's pretty much used his green shirt as often as he can without repeating outfits, because green has now been combined with all of the different pairs of pants. So excuse me, he goes on to the yellow shirt, and he can have red, and then of course he can have yellow. There we go. And blue. And he can have yellow and orange. If I were to write out these ordered pairs, what did I have? Pants first. So this would be orange, green. This one here would be red, yellow. This would be blue, yellow. And this would be orange, yellow. But in the end, the answer to the question is 6. So there are 6 outfits that he's actually bringing with him, even though he only has 5 pieces of clothing. How many of you saw pretty immediately that the answer would have been 6? And I'll ask you a question. Is it the case that you kind of ran through those combinations in your head? So if maybe not, some of you might have found a shortcut. So if I said he had 7 pairs of pants and 11 shirts, it might be more complicated. We certainly wouldn't want to do this, would we? Okay, but because the numbers are quite small, we can do that. Now, let's move on to another example in the warm-up. There's an ice cream shop or stand or cart at the beach, whatever you want to imagine. And they have a very limited supply of items because maybe they are on the beach. They're not in a retail location. And when you order an ice cream treat, you have to choose one of 2 different cones. You can choose a regular cone or a waffle cone. Regardless of the cone you select, there are only 3 types of ice cream that are available, for whatever reason. Because it's a math class, that's why there's only 3. Strawberry, vanilla, and pistachio. And you have to have sprinkles as well. So you can't, if you go there and say, well, yeah, I want a waffle cone with pistachio ice cream, but I don't want any sprinkles, they're going to turn you away. Okay, we'll talk about the option of not having sprinkles in a second. Now, if you were to try to write out all of the combinations like we did with Bobby Bear, it would be very complicated to keep track of. So we use what's called the tree diagram, and I'm going to start with the first choice that you would make. One of the choices you're going to make is, well, what type of cone? That's probably the first thing the vendor will ask you. So I'm putting R for regular and W for waffle, and you want to spread them out fairly far apart. Not so far apart that they're right at the edges of your paper. You want room on the left and the right of each of these. And if you chose a regular cone, then the person's going to say, okay, what kind of ice cream would you like? And at this point in time, your options branch out. I could choose a regular cone with strawberry ice cream, or I could choose a regular cone with vanilla ice cream, or I could choose a regular cone with pistachio ice cream. This is why we call this a tree diagram. And I can do the same thing with the waffle cone. So then you have a third decision to make. There's a third layer or a third option to your task, I'm going to call it, of buying this ice cream treat. You have to decide which type of sprinkle you want. So if you choose a regular cone with strawberry ice cream, if you choose to follow this path, you're at a fork in the road where you're going to have another choice to make. And that's why this is going to branch off now into either chocolate or mint sprinkles. And I want to pause us here and point out to you that this is one option and this is a different option. Each path from the top of your tree diagram to the bottom of the tree diagram is a choice, is one of the many different combinations. These happen to be combinations because although you can decide the answers to these three questions in different orders, it doesn't matter the order that you decide them in. You're going to get the same thing no matter what. You're not going to get sprinkles and then a cone on top of it and then the ice cream on top of that. That wouldn't make sense. And what we do is we continue to branch off here. Now, you're not going to have to do this each time, but sometimes on exams you're asked to explain what a tree diagram means. What this left-hand side of my big tree diagram means is that there are 6 different ice cream desserts, treats, that have a regular cone. Regular strawberry chocolate sprinkles, regular strawberry mint sprinkles. That's 2. Regular vanilla chocolate, regular vanilla mint. That's another 2. Regular pistachio chocolate, regular pistachio mint. That's another 2. So what we end up with is this for a tree diagram. And again, each of those branches is an option. And what that means is that each of these items at the bottom represents a different ice cream package that you're buying. So the answer, if we add those up, is 12. So the answer to this question is 12. And I know that this starts off very childlike, but don't be deceived by the simplicity of some of these. Okay? Let's look at a third option. This time you're going to go rent a vehicle. It turns out that you are in some backwater someplace in the world and they really don't have a lot of vehicles that you can rent, but the people tell you, well, you can either have a minivan or a compact car or a hybrid. Those are the 3 types of vehicles that we rent. M for minivan, C for compact, H for hybrid. Can I get blue? No. We have only 3 colors, black, red, and pink. Okay, what type of transmission would you like? Automatic or manual? And that means there's 2 choices there. So our tree diagram is going to look like this. If you choose a minivan, you have 3 different colors that you can choose from. If you choose a compact car, you have 3 different colors you can choose from. And if you choose the hybrid, you have 3 different colors. But for each of these, right now, 9 options that are on the screen. There's 9 options. Minivan black, minivan red, minivan pink. Compact black, compact red, compact pink. Hybrid black, hybrid red, hybrid pink. For each of those 9 options, you have an option of automatic or manual transmission. So it's going to standard or automatic is the words I'm using. And each of these are going to branch off. So you have to be very strategic in how you draw this, right? If I added another layer, heated seats or not heated seats, this is going to get it's going to spider web out a lot. It's going to get complicated. Anyway, when we take a look at this, this is an option. It happens to be manual, black, standard. This is a different option, manual, black, automatic. Each end point of a tree diagram is a particular option. And you're asked, well, how many, maybe option isn't the best word, is a particular decision for the entire package. And you're asked, well, how many different vehicles could you decide on? So the answer is going to be 18 when we add those all up. So do the 3 questions in the warm-up make sense in terms of how we've done this? Okay, good. In terms of the numbers, if the numbers of options became greater and there were more decisions to be made, the strategy we used for Bobby Bear is going to be out the window. And the tree diagram, although it would work, would become very complicated. And by the way, I will sometimes refer to what we're going to learn right now, the fundamental counting principle, as the Bobby Bear principle. Okay? Don't write that on a diploma exam. They probably won't know what it is you're referring to. The fundamental counting principle says that if you have a number of choices, I don't know why that's an I. I know it's not an I on your handout. It's an A, correct? Okay. I know why it's an I. That makes sense. It was an A and I wanted to change it to italics, so I went Control I, but obviously I didn't hit the Control key. This says if you have a task that you're going to complete that has multiple pieces to it, like choosing a pair of pants and a shirt, or choosing a cone and choosing an ice cream and choosing a mince or the sprinkles, that if you take the number of choices you have for each of the pieces and multiply all those numbers of choices together, you get the number of ways the task can be accomplished. So if there are A ways of doing one of the stages and B ways of doing another stage and C ways of doing the third stage, then the number of ways to do the whole thing is A times B times C. And it doesn't matter how many stages there are. If we go back to Bobby Bear, well, Bobby Bear had 2 decisions to make. He had to choose pants and he had to choose shirts. He had 3 pairs of pants and 2 different shirts. And if you multiply 3 times 2 together, you get 6. Did anybody solve that problem that way, kind of in their head? Okay. If you look at the ice cream question, you had 3 decisions to make. You weren't choosing a pair of pants and choosing a shirt. You were choosing a cone, an ice cream, and a sprinkle. And if you take the number of cones times the number of flavors of ice cream times the number of sprinkles, you get 12. So we should never have to do a tree diagram to solve these problems. It will work with any situation. This one, there were 3 models, there were 3 colors, and there were 2 transmissions. 3 times 3 times 2 is 18. So this is the fundamental counting principle. And it's used throughout most of this unit. Does anybody have any questions about the fundamental counting principle, what it means? All right, now they're going to get more complicated. So for example, and I've put Scrabble tiles down here to reinforce that we are arranging things here. The question says, how many arrangements of all of the letters of the word reason are there if you have to start with an S? So when we arrange letters, and this may be obvious to you, but later on it might not be, when you arrange letters, you can't use the same item more than once. I can't put S, 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 S. I can't do that. Okay. So we have decisions to make. Unlike Bobby Bear, who had 2 decisions, or Josh, I think, who was renting a vehicle, who had 3 decisions, we have 6 decisions. We have to decide what letter goes in the first blank, what letter goes in the second blank, what goes in the third, what letter goes in the fourth, what letter goes in the fifth, what letter goes in the sixth. But we have what's called a restriction. And the restriction is it has to start with an S. So when we do these problems, I recommend writing all of your blanks for the number of choices or number of different things you're deciding on. And then below them, writing any conditions that need to occur. This has to be an S. It has to be the letter S. These letters I was gonna say can be any letter, but they can't be any letter. You can't put an X in there because it's not in the pool of choices that we have available to us. So it's any other letter. And of course you can't repeat. There's a rule that we have to always consider that makes our lives really easy. If you have a restriction, like the restriction that the first one has to be an S, you make that choice first. And above these lines, we're going to write how many different choices we have to complete that part of the task. So what I'm saying is if the first letter has to be an S, we look down here, we see there's only one S to choose from. So we put a 1 up there. And then we move on to another decision. So this is kind of like me saying Bobby Bear is going to get dressed, but he's going to wear a green shirt. One green shirt he chooses from. But now he has to decide on the color of pants. Well, now we have to decide on a whole bunch of things. And the order in which I decide on these doesn't matter, but I typically like going left to right. So I would put a 5 here. Why do I have 5? Because as soon as I decide to put the S in there, the S is gone, right? I don't want to write the S in the blank because that might confuse some people. But the S is gone, so I'm looking now at 5 remaining items. And that means I have 5 different items I can choose from for the second blank. And now I don't know which item ends up going in the second blank. Don't fake yourself out that way. But some letter went in the second blank, which means I'm down to 4. And then I'm down to 3, and then I'm down to 2. And ultimately, I don't really have a decision to make in this question for the last blank because I have 1 letter left at that point, which means this will be 1. And because I made these 6 decisions, the fundamental counting principle says the number of ways I can complete the entire thing is found by multiplying those different numbers together, which I believe is 120. So there are 120 different arrangements of the letters of the word reason that all start with an S. In a classroom, there are 25 desks and exactly 25 students. If there were more desks than students, this question gets quite complicated. When we will have this question later where there are more desks than students, or the equivalent of it. How many different ways can those students be seated? And it turns out this is exactly the same as Bobby Bear or renting the minivan or buying the ice cream or arranging the letters of the word reason. If you just for a second assume that as teacher, I decide where everybody sits, I have 25 decisions to make. And I'm going to do this in an organized way. I'm going to say, I'm going to look down my seating plan or my attendance roster rather, and I'm going to look at all the names and I'm going to look at the first seat and I'm going to say, who do I want to sit there? And I have 25 choices to make. And I have 25 options for each of those choices. Right? I have to make 25 decisions. And for this one, I have 25 choices. So this will be 25. So I put that person's name in the list or in the seating plan and I cross them off my attendance roster, or my class list. So how many different choices do I have for the second seat that I'm going to fill? Well, 24. And by the way, I could be moving all over the place. I could say, well, I'm going to fill this one, and then I'm going to fill this one. I'm not going to do it that way. But you need to understand the order in which I pick on the seats doesn't matter. So, man, I don't want to write this. I don't want to continue to do this all the way down to the end. So I'm just going to go dot, dot, dot. And then at the end, I'm going to have 3 times 2 times 1. Right? So the answer to this question is going to be a staggeringly large number. It's going to be 25 times 24 times 23 all the way down to 1. By the way, could you think of it this way? That the students enter in and they decide where to sit. Yes, because the first person that takes a seat can choose from any one of 25 seats. The second person that physically sits down can choose from any one of 24, etc., etc. So this is the answer. Don't bother trying to calculate this. This is what you would have to do. Now, I did that, and that's what you get. But when we have times 10 to the 25, there's a lot of decimals that we are missing. We can't see what the actual number is because we're missing digits. So I ran this through Excel, and this is the number that I get when I tell Excel to show me more decimal places. Well, I don't even know how I would pronounce that number. And I can't really say 1.55 times 10 to the 25 because I'm missing information. So there is a way to abbreviate 25 times 24 times 23 all the way down to times 3 times 2 times 1. And it looks like this. And it's not 25. It's not like a surprise. That's not what the exclamation point means. It's pronounced 25 factorial. Okay. So if you have a number that you were going to multiply by 1 less and 1 less and 1 less all the way down to the end of the line to 1, it's that number factorial. And on your calculator, you do have a factorial function. Old scientific calculators, you'd just see a button on the screen that has an exclamation point. This is buried a little bit. So you enter the number of the factorial that you want to calculate. You go into your math menu, which is below the alpha key. You go over to your number submenu, and it's way at the bottom. Oh, my mistake. You go over to probability, and it's way at the bottom. Well, no, it isn't. It's number 4. I guess I'm thinking of something different. So 25 factorial is approximately this number. And again, you're getting the number that I have on my calculator that I captured for you by just multiplying all those numbers together. Right? So that's the kind of introduction to factorial notation. Let's look at number 3. If all of the letters in the word diploma are used, then I want to point out to you that all of the problems we're using today or solving today have items that are all different. You don't know what to do if I gave you a word like Mississippi that has a bunch of S's and a bunch of P's and a bunch of I's. That's for later. How many different arrangements are possible that begin and end with a vowel? So our conditions in these 7 items we're arranging is this can be an O, an I, or an A. This can be an O, an I, or an A. And I'm going to amend what I just said. It's not that this can be an O, an I, or an A. It must be an O, an I, or an A. So you have to do those conditions first. You have to make those decisions before you decide on anything else. And since there's 3 of those to choose from, then I can put the number 3 above that to represent the fact that there were 3 choices that I can make to fill in that blank. Now I'm going to put a 2 on the end. I have to do all of my conditions, all of my must-be's first. I put a 2 on the end because of those 3 vowels. I've already decided on one to go in the first blank. I don't know what went in the first blank. That's not important. If you try to think that way, you'll go crazy trying to figure out all of the options. You just have to have faith in the Bobby Bear principle. And now I say, well, I've filled in 2 options, or I've filled in 2 blanks, and there were 7 in total, so I've got 5 letters left. And I can start filling them in wherever, but again, I like to go left to right. So this will be 5 times 4 times 3 times 2 times 1, and we have to multiply all of this together, which I believe is going to give us 720. Which, on an exam, on a multiple choice, it might have this as an answer. Because 6 factorial happens to be 720. Not because you figured it out by saying 6 factorial, but because that's what it happens to be. Incidentally, this 2 times this 3 is 6. So it's 6 times 5 times 4 times 3 times 2 times 1, which is 6 factorial. Any questions with 3? 4, a volleyball team is made up of 8 players, and they're going to stand in a line for a picture. How many different arrangements are possible if Joan and Emily must be standing next to each other? So this Joan and Emily question is going to crop up in many different situations. Okay? Here they are. Janice, Sophia, Alice, Patty, Becky, Sam, Emily, and Joan. Okay? So they're going to stand in a line. But these two have to be together. So everybody, in reality, you are not really arranging 8 people. You're arranging 1, 2, 3, 4, 5, 6. You're arranging 7 items. You have to say to yourself that since Joan and Emily have to be standing next to each other, we treat them as a single item. So what we need to do is say 1, 2, 3, 4, 5, 6, 7, and ask ourselves how we can fill in these blanks. Well, who can stand at the end? Janice can stand at the end. Sophia can stand at the end. Alice can. Patty can. Becky can. Sam can. Or Joan and Emily can. 7. So this is going to be 7 times 6 times 5 times 4 times 3 times 2 times 1. But it's not going to be correct, because there's another decision that has to be made. You decide which of those 7 goes in the first place, in the second, in the third, etc. What other thing has to be decided? Let's see if anybody gets this. Mackay? What order Emily and Joan stand in? Because here they are. Are Emily and Joan together? Are they still together? Those are different. So we have to multiply whatever we got by the number of ways they can stand together. Now, I am perfectly aware that you know there's 2 different ways they can stand. But really, what we're doing is we are saying, now I have to multiply by 2 and by 1. This is the number of ways they can stand together. I'm writing it that way because if there were 3 people that had to stand together, you're not going to multiply by 3. You're going to multiply by 3, by 2, by 1. So that's how we're going to get the answer. I want to say 1680, but I could be wrong. You can do it quickly by going 7 factorial times 2. 120 times 7 is 840. Is it 1680? It's not, eh? What is it, Mackay? 1080. 10,080. 540? Okay. So 10,080. I'm sure that's right, but just make sure other people are getting the same number. Okay, good. Thank you. Better? Okay. Let's stick with this team. Janice, Becky, and Sophia must be together. So I don't want to, I didn't have time to put all the pictures and put those 3 together. But basically, you had 1, 2, 3, 4, 5, 6, 7, 8 people. But what's happening here is 3 of them have to be together. It was 8 in total, wasn't it? Okay. So let's learn a shortcut. Would you agree that I have to arrange 6 items here? Those green things I've circled. Can you accept that I don't need to write 6 blanks and go 6 times 5 times 4 times 3 times 2 times 1 and say that the number of ways to arrange the 6, I'm going to say items for fear of depersonalizing these individuals, but there are 6 items. The number of ways to arrange those 6 items is 6 factorial. And we have to arrange, the fundamental counting principle basically says the word and means multiply. That's what it says. multiply. And we have to arrange Janice, Becky, and Sophia, which would be 3 factorial because it would be blank, 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 3 times 2 times 1. I mean, I think we have to kind of get away from the concrete of writing 25 desks or 6 blanks whenever we can. So whatever we get here will be the answer. It's 4320. After a while, you will recognize certain factorials. 6 factorial is 720. So you get 4,320. Now we come to a problem which is pretty strange. Now, does yours say Joan and Emily by chance? Or does it say this? It says this, okay. Whenever you were trying to figure out how many ways to do a task where something cannot happen, you have to use this strategy that we're going to do. The first thing I want you to do is figure out how many ways these 8 players can stand in a line. I just want you to figure out, if there were no restrictions, how many ways can I line up these 8 players? And the answer is 8 factorial, right? 8 times 7 times 6, etc. So, no restrictions is 8 factorial which is 40,320. And I want to discuss, just for a second, what that number means. If you wanted to make a list of every possible way they could stand in a line, because you're interested in this kind of thing mathematically, you could take an index card and write the order of the names and put it down. And then you could take a second index card and write down a different order and put it down. And you would need 40,320 index cards. I would like you to imagine that we've done that. There's a big stack of index cards here. Every single combination or order of these players. Now what I want you to do is I want you to find out the number where Patty and Alice stand together. They hate each other. But I want you to figure out how many ways we can line them up so they do stand next to each other. With a little bit of thought, you can see that this will be the answer to the question when Joan and Emily had to stand together. Right? The fact that the names are different doesn't matter. And if these two are standing together, then you are only arranging 7 items. You're arranging Patty and Alice and the other 6 players. And then you are also arranging Patty and Alice. Was that 10,080? No, it wasn't. It was 10,080. Okay, so I want you to go back to that imaginary project where we had those 40,320 index cards, and I want you to imagine that I empty the gym and I go in the gym and I put them all face up on the floor. There's a lot of them. And then I walk around, and if Patty and Alice are standing together in that index card arrangement, I take that card and I throw it out. I pick it up off the floor and I'm going to throw it out. And I go through all 40,320 index cards, and if they are standing together, I remove them. Well, what will I be left with? I'll be left with the ones where they are not standing together, because Patty and Alice will either stand together or not. And what we say in math, in probability theory, is them standing together is the complement of them not standing together. Those two things, it has to be one or the other. And that means that the number where they're standing together plus the number where they're not together has to equal 40,320. So when you're asked for a not problem, you find a total, then you find out how many are, and take it away from the total to find out how many are not. It would be like me saying, this would be a ridiculous analogy. Well, it is a ridiculous analogy. If I want to find out how many people in the room are wearing glasses, then I can go up and down the rows, and if you're not wearing glasses, I can ask you to leave, and then I can count the people who are left, right? That's not how you would do it, but that's how you have to do it here. You cannot try to figure out, using blanks, how to arrange them so that they're always separated. It'll drive you crazy. So whatever the difference between these two numbers is the answer. Minus 10,080 gives you 30,240. And this is a far cry from the warm-up with Bobby Bear, but it uses the same principle. Any questions with C? Okay, let's take a look at number 5. We've got the letters of the word English. How many different four-letter arrangements can be formed if letters can be repeated? Wait, so we're not arranging them. What I have is an infinite number of E's. If you look up here, I could do this. I could say one of the arrangements is E. I could do that. I can use letters again and again. So I've got a whole pool of tiles that I can use. Well, how many different letters could I choose from for the first blank? 4. Sorry, 1, 2, 3, 4, 5, 6, 7. There's 7 letters to choose from. How many can I choose, Ben, for the second blank?
6. Oh, yeah.
I can use the same letter again, so it's 7. 7, 7. We multiply all of our options because of the fundamental counting principle and get 7 raised to the 4. And quite frankly, I don't care what 7 raised to the 4 is. 7 raised to the 4 might be the answer to the question, because it could be this. Numerical response question. The number of ways to do this is A to the B. Record A and B. Right? We can certainly figure out what 7 to the 4 is. It's not a Herculean task. It's 2401, if you're interested in the actual number. No letters can be repeated, and there are no further restrictions. So how many choices do I have to fill in the first blank? There's no restrictions. It doesn't say it has to start with a particular letter. So I guess this would be 7. And then 6, and then 5, and then 4, and not 3 times 2 times 1, because some of the letters don't get used. We're only making 4 letter arrangements out of 7. 840. So this works out to, when you multiply them because of the fundamental counting principle, 840. The next question is still under the umbrella of B, where we cannot repeat letters, but now we cannot repeat letters and the first letter must be an E. Well, if this has to be an E, then the number of ways to accomplish that task is 1. And again, we're arranging letters here now. I can't use an E again. And then I have 6 left, and 5, and 4. Uh, 120. So there are 120 different arrangements. Number 6, you have a multiple choice exam that has 35 questions, each with 4 choices. How many different ways could I bubble in those things? I don't really feel like writing 35 blanks. But when you bubble in the answer to question 1, you just pick A, B, C, or D at random, it's going to be 4 choices. And when you bubble in question 2, it's going to be 4 choices. And question 3 will be 4 choices. And question 34 will be 4 choices, and question 35 will be 4 choices. So we have 35. I hesitate in using the word times because we're not, I guess we're multiplying 35 times, but I don't mean to imply that it's going to be 4 times 35. It's going to be 4 raised to the 35. Which, that's a crazy number. 1.2 times 10 to the 21. There's no point in even writing that down. There was a case in the school about 20 years ago where 2 students were writing a diploma exam next to each other, and one student went in with a mark below 40, and the other student went in with a mark above 90. And they had the exact same answer sheet. Like wherever the good student had an A, the student who was failing put an A. And Alberta Ed runs those numbers, and when they see 2 answer sheets come up identical like that, they look at the marks. And there is no way that a person would guess with this many different options, and you didn't even understand the math. There's no way you would guess correctly. That person got 0 on the exam because they were cheating. There was mathematical proof that they were cheating. This would never happen. Any questions with 6? So don't cheat. Number 7, car plates in a certain country. Boy, this is going to get convoluted. Consist of a letter other than I or O. That's kind of common sometimes because I's can be confused with the number 1 and O's can be confused with the number 0. So they consist of a letter, not an I or an O, followed by 3 digits. So these are going to be the 3 digits here, here, and here. The first of which cannot be 0. So how many digits are there? Well, there's 10. If you look at my hands, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 10 digits. Or 1, 2, 3, 4, 5, 6, 7, 8, 9, and the 0. But this cannot be a 0. I'm going to write the word 0. These can be any digits. I better read the question a little further. It doesn't say anything else. It just says, yeah, any 3 digits as long as the first one is not 0. Followed by 2 letters, 2 different letters. These are typically multiple choice numerical response questions. How many different license plates can you construct? Well, if the letter, we do expect students to know that in the English language there are 26 letters. If you knock the I and the O out, that means this number is 24. You have to put a digit in the next place, but it can't be a 0, which means you have 9 options. These 2 digits, there were no restrictions mentioned, and this brings up an important point. If it doesn't tell you there's some restriction, you can't assume there is one. You can't say to yourself, oh, they have to be different, unless you're told they're different. 2 different letters, 26 choices for that one, and 25 choices for that one, because you can't use the same letter in this group. This has nothing to do with the first blank. The first blank was a special blank that was a letter other than an I or an O. When you look carefully at the question, it says followed by any 2 letters. Any 2 letters as long as they're not repeated. Whatever this works out to is the answer to the question. Okay? Which is really, I don't really feel like doing this, but anybody get an answer that's 14,040,000? That's the answer. 7. Let's talk about building here 6-digit numerals. So a 6-digit numeral might be 1, 2, 3, 4, 5, 6. or 111118. But a 6-digit numeral can't start with 0. The reason a 6-digit numeral can't start with 0 is if it starts with 0, it's a 5-digit numeral. Right? If I look at this 0, 2, 4, 3, 5, 6, I've got 6 digits, but as a numeral, that's only 24,356 when we say it. So we have to build this so this is not a 0, but the numeral must be odd. Whatever number we get when we put all the digits one after the other, we have to get an odd result. Odd numbers end in odd digits. So we have to do these two first. And these two things we have to do first don't conflict with each other. Okay? Because the odd digits don't include the 0. So that first statement really has nothing to do directly with the second statement. There are 5 odd digits to choose from for the last blank. How many digits are we allowed to choose from for the first blank? You know, Ryan?
So it can be 0.
Can't be 0, that's right. Not allowed to be 0.
9.
It is 9. It doesn't say in here that you can't repeat the digits, but we know that 55237 is a 5-digit numeral. You were allowed to use the digits more than once in building a number. So all we do is we look for this first one and we say, well, it can be anything here, except for the 0, so it's 9. Yep. Does it say no repeating? Oh, it does say no repeating. I missed that. So I'm trying to decide whether I should change the question or no, I won't change the question. No repeating digits. I assumed it didn't say that, which is no excuses. I didn't read the question. So it does say, as Naya pointed out, that we cannot have repeating digits. So, Ryan, to put you on the spot again, does that change our answer here? It would be 8. Because of the 10 digits in the pool, one of them has already been selected at the end, so now we're down to 9 digits in the pool. But of those 9 digits in the pool, one of those that's still left is a 0, and we cannot have a 0 at the beginning. Okay. Ryan, you want to take a stab at how many we can choose from for the next blank?
7.
It's not 7. Because we had 10 digits in the pool, we've selected one of the odd digits for the last blank, which means we were down to 9. We chose one of those 9 that was not a 0. So we looked at 8 of them and chose one of those 8. But we're still left with 8. At this point right here, we were left with 9 digits in the pool, in the item pool. We only put the number 8 here because one of those 9 was not allowed. But whichever one that was allowed that we chose, we're still left with 8 in the pool. So for example, very specifically, let's say that in one particular situation, you chose the 3 at the end, and then you chose, of the remaining 9, you ignored the 0 and said, I'm going to choose something out of 8, and you chose this to go there. How many would you have left? 1, 2, 3, 4, 5, 6, 7, 8. Does that make sense? Okay. So we're going to have 8 here, and then we're down to 7, then we're down to 6, then we're down to 5. And again, whatever that product is going to give you, that's going to be the answer to the question. $67,200. Okay. This is number 9. Students in a math class are graphing rational functions, and all of the rational functions are this form. X minus 3 times x minus 9 over x minus a times x minus b. And they have to build a function that has a whole and an asymptote, vertical asymptote. And they are allowed to pick any digit from 0 through 9 or 1 through 0, however you look at it, for a and b. But they always have to have one whole and one vertical asymptote. So how many different functions then can they produce? Well, you can have a whole at 3 or a whole at 9. So what are we going to choose for A? Now, I'm going to introduce something to you that's going to be helpful. The fundamental counting principle says when you have and, if Bobby Bear is going to choose a shirt and a pair of pants, you multiply those two numbers together. But if Bobby Bear, and this is not the fundamental counting principle, if Bobby Bear needs to choose a shirt or a pair of pants, you would add those numbers together. If I have 3 pairs of pants and 2 shirts and I say, you have to pick a shirt or a pair of pants, you have 5 different choices. So in mathematics, multiplication is represented by the word and addition is represented by the word or. So if we have a whole at 3, that would mean that, say, for A, we need to choose a 3, and then, well, I'll ask you, could we choose a 3 for B as well and get a whole and an asymptote? Well, no, because you're going to have either a whole at 3 or an asymptote at 3. You can't have both. Those numbers have to be different. So this is not a 3, but it's also not something else. What else can it not be? Evan, do you know? Can't be a 9. Because if it's a 9, then you're going to have 2 wholes. Because then you would have x minus 9, x minus 9. So this would be 1 multiplied by 8. There's only one digit that's a 3. We call it 3. There are only 8 digits that are neither 3 nor 9, and we call them 1, 2, 4, 5, 6, 7, 8, or 0, which means there are 8 functions which will have a whole at 3 and a vertical asymptote elsewhere. And, I mean, the logic is going to be the same here. This has to be a 9. This has to be not 9. And also not 3, because if it is 3, then you have 2 wholes. So this would be 1 times 8 as well, and you get 16. That plus thing is going to be a lifesaver. Go ahead, Naya.
Would it be fine, whatever, to just add your, the variable where you only have 2 options, so instead you just put 2 different options for A and 8 different options for B?
Definitely. And the only reason I did it this way is I really want to introduce this today. And what Naya is saying is what we could have said is for the A, there are 2 choices because we need either a 3 or a 9. Right? And then I think what Naya is saying is regardless of which of those 2 we choose, there will only be 8 choices left because we can't choose the number we used out of the 3 and the 9, because then you would have we wouldn't have an asymptote and a whole. And you can't choose the other number that we didn't choose because then you would have 2 holes. Well, that's confusing. So then she said, regardless of what I do, this would be 8. The tricky thing is going to be in this unit, and it will be for me as well, it always is. You can literally have somebody who gives me a strategy and they reason it out and they tell it to me in words, and I go, you know what? I can't find fault with that strategy. This is a perfect strategy, by the way. And then I explain my strategy to the person, and they go, you know what? Your strategy makes sense. But when we use each of the strategies, we get 2 different answers, which means somebody's wrong in their thinking. But in this case, this is correct. Definitely. Have I answered your question? Okay, number 10, which I believe is the last question. I have 3 physics books, I have 4 chemistry books, and I have 5 biology books. And I have a dedicated bookshelf on my bookcase at home for science textbooks. But I'm a little OCD, so when I put them up there, I want the physics textbooks to be together, the chem textbooks to be together, and the bio textbooks to be together. How many ways can I arrange the books on the shelf with those conditions? So there are 12 books. It's not 12 factorial. That would be if I just willy-nilly put them on the shelf in any order, but I don't want to do that. Well, I have some decisions to make. One of the decisions I have to make is, what order do I put the physics textbooks in, right? They're going to be together. So I need to order the physics textbooks. And that would be 3 factorial. Do you see how writing blank, blank, blank is going to make things unnecessarily complicated? We just know that if I want to arrange 3 books together, it's 3 factorial. And I want to arrange or order the chem textbooks, which would be 4 factorial. And I want to order or arrange the bio textbooks, which would be 5 factorial. But there's something else I have to do here. I've made those major decisions, but there's another decision. It's not a pair of pants, it's not a shirt, it's not a hybrid versus a compact. What do I have to do here, Jason?
You have to order the groups.
Right, I have to order the subjects or the groups, right? So I have to order, and I'm just using the word order. Normally we say arrange, but it's shorter to write. I have to order the physics, chem, bio categories, which would be 3 factorial. And that's one that a lot of people will miss. They'll go, oh, okay, 3 factorial, 4 factorial, 5 factorial, and then they will get an answer, which is, I don't know what. I believe when you go 3 factorial times 4 factorial times 5 factorial, you get this number. But that's not the answer, and you know by now if it were multiple choice, that would be an answer. It would just be an incorrect one. You still have to multiply by 3 factorial, which is 6. So the answer to this question is 103,680. It's at this point that many of you already love this, and many of you already hate it. Okay? And I appreciate that. And the only thing I can tell you to make you enjoy it more, which would be a good thing if you enjoy doing something rather than not, is like anything else, the more different examples that you practice, the better you get at it, the more successful that you are, the easier it becomes, and it's more pleasing to you. So I'm not saying you have to do all of these. I'm not saying how many you have to do. There's 2 sets of problems dealing with